everyone. In the last video we have discussed the basic concept of complex number. So today we will see how the complex numbers are represented as far as the geometrical representation, vector representation or trigonometrical representations are concerned. So here if you consider first the geometric representation. So if we consider this geometric representation, so suppose this is your x-axis and this is y-axis and this is the origin O. Now when we say the complex number, so let us say we put a complex number z. Okay, so as far as the representation on this coordinate plane is concerned, here once we represent the complex number z, so there are real part as well as the imaginary part. Real parts it will be plotted along x-axis and the imaginary part it is plotted along the y-axis. So in this case x-axis will be considered as the real axis, y-axis it is considered as the imaginary axis. So if we consider this z and its coordinate is suppose x and y, let us say coordinate of this complex number z it is x, y. So when we say coordinate is x and y, it means along the real axis x, its distance is x, and along y-axis, that is the imaginary axis, its distance is y. Now, so this becomes your real axis and this becomes the imaginary axis. So obviously the combination of this real axis and the imaginary axis, or the real plane and the imaginary plane, that makes it complex plane. And this complex plane is also termed as the Argand's plane. This is also termed as Argand's plane. Here you can see Argand plane. So this complex plane, which is combination of the real axis as well as the imaginary axis, that is termed as the Argand plane. Now any diagram drawn in this plane, Argand plane or the complex plane, that will be termed as Argand's diagram. So that is also termed as the Argand's diagram. So Argand plane, Argand diagram, it is nothing but the combination of real axis as well as the imaginary axis. Otherwise everything remains same. The representation along x-axis as well as along y-axis, as we do in simple coordinate geometry, similarly here also we will be doing the same thing. Now if this point is suppose z and its coordinate is xy, here O is the origin, so you can consider this OZ. Okay. So if we drop this perpendicular from here, so this part it will be your x and this part it will be y, as we do in simple coordinate. This is your x and this is y. So this is the coordinate representation of the complex number. We call it as OZ. So these are just the representation. We can, so this is your first plane, second plane, third plane and fourth plane. So this is in the first quadrant. So we have this. Similarly z could have been here in the second quadrant, in the third quadrant, in the fourth quadrant and so on. So that way we represent as far as the representation or the coordinate representation is concerned. Here this is your right angle triangle. So here this is x and this is y. So if you consider this distance as r, then we can say r it is equal to x square plus y square square root. This r it is the square root of x square plus y square. So here if you consider that this angle is theta, suppose this is theta, then tan theta in this right angle triangle will be how much? Y upon this x. So tan theta we can say it is equal to your y upon x. Y is what? Now let us generalize. Y is the imaginary part of the complex number and x is the real part of the complex number. So we can say that this is imaginary of z upon real of z. So this becomes a general representation. Yani tan theta is always the imaginary part. Always you can't say it is just x or this y. It can be some different term. So it is always the imaginary part divided by the real part. So tan theta is this, r it is equal to this. Now this r, it is also termed as the magnitude of this complex number, because this r is the distance here along this line. which is at an angle of theta with the x-axis. So r is termed as the magnitude of the complex number, and theta is termed as the argument or amplitude of the complex number. This theta is termed as the argument or amplitude of the complex number. R is termed as the magnitude of the complex number. Now, if you have this complex number z, then its magnitude is represented as mod of z with these two vertical bars, as we do in simple algebra. So z, it is mod of z is the magnitude of the complex number, and that is equal to your square root of x square plus y square square root. So here we can write this is equal to mod of z. So this is the geometrical representation of the complex number. XY plane, x is along the real axis, y is along the imaginary axis. Combination of this, it becomes a complex plane. That complex plane is termed as the Argand plane. Any diagram drawn in this Argand diagram, that will be termed as the Argand's diagram. So here you can see on this. Now, so this angle, we have assumed this, here you can see this diagram again. So this angle we have taken as theta. This is the magnitude, that is r. Okay, coordinate p, x, y, that is your z, x-axis as well as y-axis, and this is the origin. Absolute length OP, that is the distance, that is square root of x square plus y square, that is termed as the modulus or magnitude of the complex number, represented by mod of z. So we have all this relation, and amplitude theta, it is tan theta is equal to imaginary part upon the real part. When tan theta is equal to, suppose, y upon x, so theta obviously is how? Tan inverse upon y upon x. So we have tan inverse y upon this x. So this way we represent all this. Now from here, so from here we can also have the vector representation. So if you recall the concept of the vector, so suppose again this is your x-axis and this is y-axis. How do we represent the vector? If suppose you have this vector, let us say position vector OP. So we write xi plus yj. If we consider the two-dimensional, if we consider three-dimensional, then it will be xi plus yj plus zk. That means what? X and y is the coordinate of the point P. Suppose you have this point P, its coordinate is xy. Okay, so this is your OP. So now as far as the vector representation of this point is concerned, we say it is xi plus yj, because along x-axis we take the unit vector I, along y-axis we take the unit vector j. So we represent xi plus yj. Now you can see the similarity. This is the vector representation. As far as the complex number is concerned, we represent a plus ib. Now here you have this unit vector I and j, and here we have the real part and the imaginary part. If this coordinate is xy or this coordinate is suppose ab, how we will represent this complex number p? If p is complex, then how we will represent a plus ib? If you have this vector as OP, the vector representation, we represent xi plus yj. We say this is the unit vector I, unit vector j. It is the coefficient along x-axis, this is the coefficient along y-axis. Similarly, here it is the real part as well as this is the imaginary part. This is the only difference. Here we use the word unit vectors, here we use the word real axis as well as the imaginary axis. So that is the only difference. Otherwise everything remains same. Here also if you consider this angle as theta, so you will say this vector makes angle theta with the x-axis such that tan theta is equal to this distance upon this distance, means y upon this x. Magnitude of this vector, again it is x square plus y square square root. So every concept remains same. That's why we say the complex number is nothing but its behavior is as equivalent as the behavior of a vector, and magnitude remains same, amplitude or the angle that it makes, that remains same as far as the calculation or representation part is concerned. So that's why it is also termed as the vector representation. I hope it is clear. Now let us consider the trigonometrical representation. So just now we have seen if you see this diagram here, so here from this only we can have the trigonometrical representation. This angle is theta and this magnitude is r. So this will be equal to how much? If you drop this perpendicular, and if this is r and this is theta, then this becomes your r cos theta and this becomes r sin theta. This is r cos theta and r sin theta. This geometrical representation, the coordinate was x, y or ab. So we can say z is equal to a plus ib. Vector representation, we have xi plus yj, taking help of, as far as the position vector representation is concerned, taking help of unit vector I and j, we write xi plus yj. Similarly, that is as equivalent as the representation of this complex number. It is as equivalent as the vector representation. The only thing is, instead of unit vector I and j, we consider what? We consider the real part as well as the imaginary part, that is x plus iy. Now let us come to the trigonometrical part. Here the magnitude is r, this angle is theta, so this becomes your r cos theta and this becomes r sin theta. If z is your complex number, then z we write x plus iy. Here x is equal to how much? R cos theta. So this becomes your r cos theta, plus y is equal to how much? R sin theta. So plus I r sin theta. You can take this common, so this becomes r cos theta plus I sin theta. This is the trigonometrical representation of the complex number z. So z is equal to r cos theta plus this I sin theta. So we call this as the trigonometrical, because now here we have this cos theta and sin theta all trigonometrical term. So this becomes your trigonometrical representation of the complex number. R is the magnitude or modulus of the complex number, theta is the amplitude or argument of the complex number, and theta, as we have just now calculated, tan theta is what? Tan theta is always imaginary of z and divided by this real of z, that means y upon this x. So that way we can calculate this theta. Now here, when you have this angle theta, so either this can be in the first quadrant, this can be in the second quadrant, it can be in the third, and it can be in the fourth. Depending on in which quadrant this complex number z is, depending on that we calculate the value of this theta. So that will depend in which quadrant, what is the principal value of theta, and corresponding to that in which quadrant this z lies, so that we can calculate this theta either using the concept of what? Pi or this 2 pi. So that we will be discussing when we start simplifying the questions, like suppose z is in this quadrant, this or this, accordingly what will be value of the amplitude or the argument of that complex number. So this you can see here, magnitude x square plus y square r square, that we have just discussed. So that way, just to summarize all this, P, if there is a point P, just one second. If there is a point P in the xy plane, and corresponding to that the complex number and its coordinate is suppose xy, then the complex number it is x plus iy. This we call it as the algebraic representation of a complex number. Z is equal to x plus iy, a plus ib, c plus id, and so on. The same it can be represented in the vector form or the geometrical form. So if you have this point P and its coordinate is x and y, so we say the coordinate of the point P is xy and it is at some angle theta with the x-axis. So this becomes your geometrical representation. Third is the vector representation. Vector and geometrical, they are equivalent to each other, because here the only difference is there we will take help of the unit vectors I and j in vector to represent the position vector of any vector, and here to represent the vector P we just say that it is the real axis, this is the imaginary axis. We have real part as well as the imaginary part, and corresponding to that we have the equivalent relation. Third comes the trigonometrical representation. Now again we know if this distance is r and this angle is theta, this becomes your r cos theta, this becomes r sin theta. X will be replaced by r cos theta, y is replaced by r sin theta, and corresponding to that we get j is equal to r cos theta plus I sin theta. That is termed as the trigonometrical representation. So these are the things that we have understood today. So magnitude of z, it is x square plus y square square root. Amplitude of z, if it is theta, then tan theta, it is imaginary part of z divided by the real part of z. We have the concept of the conjugate of the complex number. If z is equal to your x plus iy, then z bar it will be equal to x minus iy. So apart from this, we have the Euler's relation, we have de Moivre's theorem. So all these things we will discuss in the next video, and after that we will start simplifying problems based on complex number. Thank you.